Welcome to lesson 18 on power system analysis. In this lesson, we will continue with our discussion on power flow solution methods. In the last lesson, we discussed about the Gauss-Seidel method for power flow solution. In this, we will continue with some of those aspects, and then we will talk about newer method for power flow solution. Well, in this lesson we will start with some computational aspects of Gauss-Seidel method, then we will talk about power flow solution by Newton-Raphson method. We will then talk about direct solution of linear algebraic equation, as we will find that Newton-Raphson method finally boils down to solving a set of linear algebraic equations, and then we will take a small example of solving this linear algebraic equation by the Gauss elimination method. Well, the objective of this lesson is that at the end of this lesson you should be able to explain the characteristics of the Gauss-Seidel method, develop Newton-Raphson iterative technique for power flow solution. You should be able to solve a set of linear algebraic equation and solve power flow problem using Newton-Raphson method. Of course, this part we will take up in the next lesson, as well as we will take up some example there. Well, as we discussed in the last lesson, the algorithm steps for Gauss-Seidel method are: first, what we need to do is find out the bus injections Pi and Qi. From the known values of generation, that is Pgi, Qgi, and the loads Pdi and Qdi at bus I. So, once we know these quantities, we can calculate Pi and Qi. Pi will be Pgi minus Pdi, and Qgi minus Qdi will be Qi. So, we first need to calculate the bus injections. After that, we need to form the Y bus matrix for the power network. Then we will set the initial voltages. As we said in the last lesson, normally we use a flat voltage start where the magnitude Vi is set as 1 per unit and the angle delta I is set as 0 degrees. After we have set the initial voltage values, we iteratively solve the equation given here. Vk at iteration I plus 1 is equal to 1 by Ykk into Pk minus jQk by Vk conjugate at iteration I minus summation Ykn Vn at iteration I plus 1 from for n is equal to 1 to k minus 1, and plus summation Ykn into Vn I for n is equal to k plus 1 to n. Now, here what we are saying is we are trying to use the latest available value. So, if we are solving for equation number say 5, where k is 5, then V5 if we are solving, then we already have solved for V1, V2, V3, V4. So, in that case what we have is for V1, V2, V3, V4 we will be putting the latest value, that is I plus 1th iteration values, whereas for other voltages, that is V6 to Vn, we will be having only ith iteration values available. So, we will substitute those values and obtain new value, that is at I plus 1th iteration for V5. So, in this way, for all the voltages we need to solve this equation and obtain the new values like this, and we will continue this iterative solution till V k I plus 1 minus V k I, that is the values for k plus 1th iteration I plus 1th iteration and ith iteration are very nearly equal. That is, the difference between them is very small or less than a set value which we have used as a tolerance level. So, this iterative solution is carried out till we have a convergence obtained or the values change is less than the tolerance value that we have specified. Now, we will talk about computational characteristics of Gauss-Seidel method. Gauss-Seidel algorithm has one problem, that its convergence is somewhat slow, in the sense that if you have a very large system, suppose you are having a system with more than 100 buses or a 100 bus system, let us take for example, then the number of iterations which one needs to solve these load flow equations for 100 buses, we will have 100 equations to be solved, and normally this will take the number of iterations to reach a reasonable convergence will be also of the same order, that is about 100 iterations. So, as the system size becomes larger and larger, the number of iterations also keep on increasing for this kind of a method, and this is one of the reasons why this method is not so much preferred nowadays for very large system analysis. Of course, we can accelerate the convergence to some extent by using an acceleration factor. So, what we do is that we have the updates x I plus 1 is equal to x I plus delta x at iteration I. So, what we do is, instead of adding this delta x, that is what we have is x I plus 1 minus x I, that is whatever value we have got, say for V k at I plus 1, and this value for V k at I is known. So, V k at I plus 1 minus V k at I will give me the value of delta V k. Now, delta V k at iteration I. Now, this, instead of using this value, what we do is we add, instead of delta x I or delta V I, we are adding alpha times delta V I to obtain this V at I plus 1. So, if we are doing that, then what we are doing is we are trying to reach the solution faster or accelerate the process of iteration. Now, this has two aspects. Sometimes this can lead to divergence as well. If you choose the value of alpha very large, then what can result is a divergence, that is, you may not reach any convergent solution at all. Though in many cases, if we use this alpha in the range of 1.5 to 1.7, it has been found that generally these values will provide much better convergence than if we are using no acceleration, that is alpha is equal to 1 only. So, some acceleration of Gauss-Seidel algorithm can be achieved by using an acceleration factor added to the updates that we get. However, this still is not very good for large system analysis, because still the number of iterations required is much larger, and that therefore, the time needed for the solution is much larger, and therefore, there was search for better methods for solving this load flow or the power flow problem. And one of the methods which provides almost constant number of iterations for any size of system. That is, the number of iteration is independent of the size, almost independent of the size of the system. One of the method which provides this kind of a property is the Newton-Raphson method. So, we will talk now. So, we will see how we apply Newton-Raphson method to power flow analysis. Now, here as we had seen, if we write the power flow equation for each bus in terms of power injections, real power injection and reactive power injection separately, then we get real power injection P k is equal to V k summation y k n V n cos delta k minus delta n minus theta k n for n is equal to 1 to capital N, where capital N is the number of buses and delta k and delta n are the voltage angle associated with the voltage at bus k and bus n. Theta k n, I am sorry, this should read theta k n, theta k n is the angle of admittance y k n. Similarly, the reactive power injection at bus k will be given by V k summation y k n V n sin delta k minus delta n minus theta k n for n is equal to 1 to capital N. So, these two equations are basically providing us a relationship between power injection at any bus k and the voltage magnitudes and the network parameters. Now, we can write this equation as in a general form as y is equal to f x, where f x is a vector f 1, f 2, f 3 up to f n. That is, for each bus we have one function which relates the real power and reactive power at that bus. So, we have n such functions. So, y is equal to f x is the general form of this equation. Now, if we where we have y equal to p and q, vector p and q are basically from p 2 to p n, p 2 p 3 up to p n, and q will be from q 2 to q n, that is q 2, q 3, q 4 up to q n. Now, here what we have done is we have assumed that bus 1 is a swing bus or a slack bus. That is, for this bus we have specified the voltage magnitude as well as its angle, that is, this is a reference bus. So, its angle is generally assumed to be 0 and the voltage magnitude is also specified for this bus. We had already discussed why we need this swing bus in the system for power flow analysis. So, this is y is this a vector of p's and q's, and x is a vector of the voltage angle and the voltage magnitude, which again can be written as a vector from delta 2 up to delta n, that is delta 2, delta 3, delta 4 up to delta n, and V 2 to V n, that is V 2, V 3, V 4 up to V n for all the n buses in the system. Since delta 1 is 0 and V 1 is specified, which is normally 1 or maybe very near to 1, whatever value it is, that value is specified. Therefore, we can write f x is equal to p x q x, where we p x q x or this vector f x is p 2 a function of x up to p n, all these are function of x, q 2 to q n, all these are also function of x, where x is basically the voltage angle delta and the voltage magnitude V at all the buses. So, now we can write y k, that is the element kth element of this y matrix will be y k is equal to p k, which is a function of x. So, we can write it as p k in bracket this x, that is p k is a function of x, and this is equal to v k summation y k n v n cos delta k minus delta n minus theta k, and this is already we have explained. From summation is up from n is equal to 1 to capital N. Now, y k plus n is q k, that is we have, since we had arranged our y in such a way that from 2 to n we have p, and then after that n plus 2 to 2n we have the q values. We have no values for 1 p 1 and no value for q 1, because this is bus 1 is a slack bus. So, we have y k plus n is equal to q k is equal to q k, a function of x, which we can, as we have seen earlier, can be written as v k summation y k n v n sin delta k minus delta n minus theta k n for k varying from 2 to n, that is for all the buses except the slack bus, which is bus 1 in our case. Now, if we make an initial guess x is equal to x 0 and then use the Taylor series expansion for f x about this initial guess of the state x, then we can write y is equal to f x 0 plus df by dx at x is equal to x 0 into x minus x 0 plus higher order terms will be there, that is d 2 f by dx 2 factorial 1 by 2 x minus x 0 square, all those terms, higher order terms will be there. Now, if we neglect the higher order terms, that is if we are assuming that our x 0 is close to the true value x, then x minus x 0 square and x minus x 0 cube, all those terms are going to be much smaller, and therefore, they can be neglected. So, neglecting higher order terms and solving for x, we get the solution as x is equal to x 0 plus df by dx at x is equal to x 0 inverse into y minus f x 0. That is from this expression itself. If we forget these terms, then we can write this x on this side, and we can take this x 0 on this side. So, we have x 0 and this y minus f x 0 we can write here. So, y minus f x 0 will be this side, and then df by dx at x is equal to x 0 into x minus x 0 is there. So, then again taking this x 0 on this side. So, we will have x is equal to x 0 plus df by dx inverse into y minus f x 0. So, what we are doing is taking this f x 0 on this side. So, y minus f x 0, and then we are pre-multiplying it by the inverse of this. So, we get df by dx inverse into y minus f x 0, that will be equal to x minus x 0. Therefore, x is equal to x 0 plus this term. So, this is what we get as the solution for x. Now, since our guess may not be very close, therefore, what we do is try to solve this using an iterative method. So, the iterative solution, this for iterative solution, this equation becomes like this: x for I plus 1th iteration is equal to the value of x for I plus 1th iteration is equal to the value of x at ith iteration plus j inverse, where we are writing df by dx inverse as j inverse. So, df by dx is our j. So, this is j inverse at ith iteration into y minus f x at ith iteration. So, this is the iterative solution that we will get for at each step, that is at each iteration we will update x, and we will keep doing it till we reach a convergence, that is x I plus 1 minus x I becomes very small or becomes less than our specified tolerance. Now, here as I said earlier, this j is computed, or j I is basically the value of the first order derivative df by dx for x is equal to x at ith iteration. So, substituting the value of x at ith iteration in the equation and taking its derivative, we will get the j I, that is. So, j I can be defined as del f by del x I, del f 1 by del f 1 by del x 1, del f 1 by del x 2, that is for all the n equations that we have, we will have these partial derivatives of f with respect to x, and that is x 1 up to x n. So, we will have del f 1 by del x 1, del f 1 by del x 2, and so on, like del f 1 by del x n. Similarly, for the second set of equation, that is del f 2 by del x 1, del f 2 by del x 2, del f 2 by del x n, and so on till the nth equation we have is del f n by del x 1, del f n by del x 2, and so on till del f n by del x n. This all we are calculating by substituting the value of x at ith iteration, that is with x is equal to x I. Now, this equation, as we have seen here, x, the updated value or the next iteration value x I plus 1 is equal to x at ith iteration plus j inverse at ith iteration into y minus f x I. Now, here we have got a j inverse term, and as we have seen, j is n by n matrix. In our case, since we are having n buses in a system, if we have n number of buses in a system, then we have how many equations? We have, except for the slack bus, we have 2 equations for each bus. So, that is if we are assuming that all the buses are PQ buses. So, total number of equations that we have will be equal to 2 into n minus 1. So, that is for a 100 bus system, we will have 2 into n minus 1, that is 99, that is 198 equations. So, we will have a 198 by 198 matrix representing this J. Now, this matrix is a large matrix. For a large system, this will be even much larger matrix. So, if we see, as we see here, we need an inverse, and finding out an inverse for a very large matrix is very time consuming process. So, in power system applications, we generally do not find the inverse of the matrix, rather we try to solve it by using some other means. We will see how we do that. So, this equation contains the matrix inverse J inverse. Instead of computing J inverse, one can rewrite the above equation as follows. That is, this equation can be rewritten now. That is, if we write x I plus 1 minus x I as delta x, then we have, if we take this on this side, then we have j I into delta x I is equal to y minus f x I is nothing but delta y. So, is equal to delta y, where we are writing delta x I is the x I plus 1 minus x I, and delta y I is y minus f x at I, or ith iteration. So, if what we are seeing here is, now we have a set of equations which can be written in this form, where we do not have the inverse of J, but we have J matrix. Now, we need to solve for delta x using this equation. Now, if we look at this equation, that is J I delta x I is equal to delta y I, is of the form A x is equal to y, where A is this matrix J. Instead of J, we are writing here as a general form. This is of the form A, which is a n by n matrix. X delta x here is the x values, is equal to y, that these are the delta y values which will be there. So, at each iteration, what we need to do is solve a set of equations A x is equal to y. These are a set of linear algebraic equations. So, basically, if we look at the Newton-Raphson iterative scheme, then what we see is, this is the solution that we need to obtain. This x I plus 1 is what we need to get. We can get delta x I by solving this sort of an equation, or a set of linear algebraic equation, and once we know this delta x, knowing x at ith iteration and knowing delta x at ith iteration, we can get x I plus 1 is equal to x I plus delta x I. Therefore, we can always get the updates in each iteration. So, if you see, the Newton-Raphson solution method finally boils down to solving a set of linear algebraic equation. That is, what we have done is, a set of nonlinear algebraic equations are being solved as a set of linear algebraic equation, where we are linearizing the equation at each and every step of iteration. Now, how do we solve this set of equations? That is, this A x is equal to y. How do we solve this kind of a system of equation? Now, what we need to do for this is, if we can, one method, as we said earlier, is take the inverse of A, pre-multiply it on both sides, then x is equal to A inverse y. That is the easiest way to do it, but since finding inverse is computationally much more complex and time consuming. In fact, finding inverse for a n by n matrix, the time required is proportional to n cube. So, if the size of the matrix increases, the computation time for finding inverse also increases much more. Therefore, instead of finding inverse in that way, we need to find some other way of solving it, and one of the ways, as we said here, is direct solution of linear algebraic equation using Gauss elimination method. So, here we are trying to see how we can use Gauss elimination to solve this set of equation. Now, what this Gauss elimination tries to do is, tries to triangularize this matrix A, which is a n by n matrix, into an upper triangular matrix. That is, all the elements below this diagonal A11, A22, ANN are made 0. So, all the elements here A22, A21 up to AN1, then A23, sorry, A32 up to AN2, and so on, all these will be made 0. If we can do that, then we get an upper triangular matrix as shown here, where all the elements below the diagonal are 0. Now, if we can do this kind of a thing, then finding the solution for this set of equation is very easy, because you can see we know this y n if we want to find out x n, then we have from the last equation a n n is equal a n n into x n is equal to y n. So, x n is equal to y n by a n n, and once we know this value of x n, then we can substitute this value into this location, because here we have a n minus 1 into n minus 1 into x n minus 1 plus a n minus 1 into n into a x into x n is equal to y n minus 1. So, knowing this value, substituting it here, we have only one unknown x n minus 1, which can be again found out, and so on. We can proceed backward from the nth element, and finally we can go up to the first element, and therefore we can find out all the unknowns x 1 to x n. So, this is what we call the back substitution method. So, here, as I said earlier, x n will be given by y n divided by a n n, x n minus 1 will be given by y n minus 1 minus a n minus 1 into n into x n. Now, x n value is already known from here, divided by a n minus 1 into a n minus 1. Similar way, we can write for any general element x k, this will be equal to y k minus summation a k n into x n for n is equal to k plus 1 to n divided by a k k for k is equal to n, n minus 1, so on up to 1. That is, we proceed backward from nth element to the first element, that is, starting with the last equation, we go backward up to the first equation. In this way, we can find out all the unknowns x. Now, how do we triangularize this matrix? That is the problem that we have now. So, in Gauss elimination, what we try to do is, since we have this, first we have this matrix A here like this. Okay. Now, what we want to do is, first we will try to make all these elements below A 1 1 as 0. Now, for doing this, what we can do is, we can multiply this row by A 2 1 and then subtract from this. We will see how we do that. That is, we can multiply this row by A 2 1 by A 1 1. Okay. So, we multiply this row by A 2 1 by A 1 1 and then subtract from the second row, then we will get this as A 2 1 minus A 2 1. So, this becomes 0. This element will be A 2 2 minus A 2 1 by A 1 1, which is this, all the elements of this row has been multiplied by that, into A 1 2 will be the element of this row. So, A 2 2 minus this element will be the new element at this position, and so on for A 2 n minus A 2 1 by A 1 1 into A 1 n will be this element when we multiply this row by A 2 1 by A 1 1. So, when we subtract it, this will be the new value of the element A 2 n. Similarly, for the third row, we multiply this by A 3 1 by A 1 1 and then subtract from the third row elements. So, all the elements of row first, row 1 is multiplied by A 3 1 by A 1 1 and then it is subtracted from the third row, and so on. We can do it up to nth row, then what we will get is zeros in the first column below A 1 1. So, all the rows here we can eliminate the first column elements like this. So, we can write this. When we are doing this, of course, we are also multiplying and doing the same subtraction for the y also. So, we have y 2 is equal to A 2 1 by A11 into y1, y3 will be equal to y3 minus A31 into A11 into y1, and so on up to yn minus an1 by A11 into y1. So, the column vector y of the known variables is also getting modified in the same way. So, now what we have after we have done this process, after we have done this process, then we can rewrite these elements as A221, A2n1, that is the modified value after the first step of elimination, that is the first step of triangularization. We get all these elements, modified elements, that we can write as with a superscript 1 here. So, this is now the set of equations that we have, where this y's are also modified values. Now, what we need to do now is below A22, all the elements in the second column have to be made 0. So, in the same fashion, we can multiply the second row by A32 by A22 and then subtract from the third row, and so on. That is, for fourth row, A42 by A22 we will multiply this row and then subtract from the fourth row, and so on. So, if we do that, then what we will get is all the elements in column 2 will become 0, and the same way we have to modify the column vector y also. So, we will get a new set of y's. Of course, y1 will remain same, y2 will remain whatever as y21, but we are writing this new values because all the rows which are already below which the diagonal of which we have already eliminated other elements are not to be processed again. So, this row is not getting processed, only this row we had processed using this row all the rows below this or all the equation below this, and so on. If we can do that, then finally we will get a triangular matrix. So, we can write this process as such. During step k, we start with a k minus 1 x is equal to y k minus 1. That is this is k minus 1 is the already affected elements that we have done at k minus 1th step. So, a k minus 1 x is equal to y k minus 1. The first k of these equations already triangularized are left unchanged. As we have seen here, if we have already triangularized this row, so when we are taking the second equation, we do not do anything to the first equation. When we are taking the third equation, then first and second, which have already been triangularized, will be left unchanged. So, like you see here, this is not changed, only below this all are getting changed. So, are left unchanged. Also, equation k is multiplied by a n k at for the k minus 1th value, whatever is available, divided by a k k at k minus 1th value, and then subtracted from equation n for n is equal to k plus 1, k plus 2 up to capital N. So, this is the process that we follow, that is, we take equations one by one and we eliminate the columns for them, that is, all the elements in the column below the diagonal are reduced to 0. So, this is how we process it, and so after n minus 1 steps we arrive at the equivalent equation a n minus 1 x is equal to y n minus 1, where A n minus 1 is the upper triangular matrix. So, this is the way we work with the Gauss elimination method. So, by using this Gauss elimination method, what we are doing is we are triangularizing the matrix and obtaining an upper triangular matrix. Once we have this upper triangular matrix, then we can find out the value for x, the unknowns which we need to find out in A x is equal to y. So, let us take a small example. Here we have a 3 by 3 matrix. Our A matrix is a 3 by 3 matrix. The first row is having 2 3 minus 1, that is the equation that we have is 2 x 1 plus 3 x 2 minus x 3 is equal to 5. The second equation we have is minus 4 x 1 plus 6 x 2 plus 8 x 3 is equal to 7. The third equation is 10 x 1 plus 12 x 2 plus 14 x 3 is equal to 9. So, in matrix form we write this. This is our A matrix, this is the unknowns x 1, x 2, x 3 that we need to find out, and this is the y vector for which the values are known. Now, what we do? We need to triangularize this matrix, that is these elements, these 3 elements need to be eliminated. So, what we do? First we take this matrix. Now, first row is like this, we do not need to do anything to the first row. We need to eliminate this or make this 0. So, what we are going to do is we are going to multiply this row by A 21 divided by A 11. So, A 21 divided by A 11 will be equal to minus 4 divided by 2. So, that is equal to minus 2. So, we are multiplying this equation by minus 2 and subtracting it from this. So, when we minus 2 into 2 is minus 4. So, when we subtract it from minus 4 we get 0. Then here we have 6 minus 2 multiplied by 3. So, 6 minus 2 multiplied by 3, and here we will have 8 minus 2 multiplied by this minus 1. So, this is the value that we will get. Then again for eliminating this we have to multiply this by 10 by 2, that is 5. So, multiply this equation by 5, then we get 10, here we get 15, here we get minus 5. So, when we subtract it from this we get 0 here, then 12 minus this is 15, that is 5 into minus 5 into 3, and this is 1 into 5. So, that is minus 1 into 5. So, here we have 14 minus 5 into minus 1. So, this is what we get. Now, when we are doing this equation we also have to work on this. So, here we had multiplied this equation by that is we have multiplied this equation by minus 2 and then subtracted from this. So, 7 minus 2 into 5. So, minus 2 into 5, this equation is multiplied by minus 2. So, this becomes minus 2 into 5, that is subtracted from 7. Similarly, when we are eliminating this we have multiplied this equation by 5. So, what we have is 9 minus 5 into 5 when we multiply this equation by 5. So, 5 into 5. So, 9 minus 5 into 5. So, this if we do we get this set of equation now as 2 3 minus 1, this row does not get changed, these two values have become 0. This is from here 6 minus 6, that is 6 plus 6 12, 8 plus 2. So, this is plus 2. So, 8 minus 2, that is 6. So, what we have here is this, I am sorry, yeah, that is 12, and this term is 8 minus 2 6. So, this is 6, then this term is 0, this term is now this term is 12 minus 15. So, that is minus 3, and this term is 14 plus 5, that is 19. So, we get minus 3 and 19, and these terms are similarly 7 minus of minus 10, that makes it 17, 9 minus 10, that makes it 9 minus 25, that makes it 16. So, we have minus 16 here, 5, 17 and minus 16. So, now this is the set of equation that we have. Now, what we need to do is eliminate this element, so that we get a triangular matrix, upper triangular matrix. So, for eliminating this element, what we do is we multiply this equation by minus 3 by 12 and subtract from this. So, minus 3 by 12 is minus 0.25 or minus 1 by 4. So, we multiply this equation by minus 0.25 and subtract from this, then this becomes 0 and we have this 19 minus 0.25 into 6. So, this is what we have got here, and here what we have is minus 0.25 into 17 have to be subtracted from this minus 16. So, minus 16 minus 0.25 into 17. When we do this, we get finally our set of equations as 2, 3, minus 1, 0, 12, 6, 0, 0, 10.5. Now, you see this is a triangularized matrix, and the y vector is also modified as 5, 17, minus 11.75. Now, once we have this set of equation, now what we need to do is find out x 1, x 2, x 3. So, we will use the back substitution method. So, if you see here, we have 20.5 x 3 is equal to minus 11.75. So, x 3 is equal to minus 11.75 divided by 20.5. So, once we know the value of x 3, then from this equation we have 12 x 2 plus 6 x 3. So, 6 x 3 we can substitute the value here is equal to 17. So, that can be brought on this side, then 12 x 2 we have. So, divide this side by 12, you will get the value of x 2. Once we know x 3 and x 2, we can find out the value of x 1, because this equation is 2 x 1 plus 3 x 2 minus x 3 is equal to 5. So, we can, since we know x 2 and x 3, the only unknown here is x 1. So, we can find that from that equation. So, this is how we solve a linear set of equations, and this Gauss elimination method is one which is preferred. There are other methods of solving this linear set of equations, which we call methods of decomposition. That is, we factorize this matrix A into lower and upper triangular matrices, that is LU factorization. Sometimes we use LDU factorizations. There are other methods which are called bifactorization method. All these methods, basic idea is to avoid using inverse and try to find out the solution for Ax is equal to y using a direct solution method, that is by trying to factorize the matrix. So, this is, of course, Gauss elimination is the simplest of these methods and is quite effective and is very much used for solving linear set of equations which come out from the Newton-Raphson load flow equations. So, this is what we will do today, and in the next class we will talk how to solve the Newton-Raphson power flow equation using this direct solution method. So, that is all for today, and thank you very much. Welcome to lesson 19 on power system analysis. In this lesson we will continue with power flow analysis. In this lesson we will talk about the computation of Jacobian matrix for Newton-Raphson method. Then we will talk about the computational algorithm for Newton-Raphson power flow, and we will work out one example for a small power system, how we do a Newton-Raphson load flow or power flow. Well, once you complete this lesson, you will be able to compute the elements of the Jacobian matrix. You will be able to develop the Newton-Raphson power flow algorithm and solve power flow problems using Newton-Raphson method. Before we go into the computation of Jacobian matrix elements, we will recapitulate some of the equations for that we developed for the Newton-Raphson load flow or power flow. Well, as we had seen in the last lesson, the power flow equations in terms of real and reactive power injections at any bus K is given by these relationships. So, which is a function of voltage magnitude at all the buses and the voltage angle at all the buses, as well as the admittance magnitude and angle for the transmission network. Same is true for the reactive power. The equations can be written as shown here. We can write this as a function of x as y is equal to fx, where for each bus we will be writing these two equations. So, if there are number of buses, then we will write all these equations as f1 x up to fn x, total number of equations required, where y is basically a vector of real power injections P and reactive power injections Q. Here we have assumed that bus 1 is a slack bus for our purpose. So, for slack bus, since we know the voltage magnitude and angle, we do not have any real power or reactive power specified. So, we do not have any P1 and Q1 in this vector of y. So, we have P2 to Pn and Q2 to Qn. The unknown vector or the state vector is given by the voltage phase angle delta, and V, again this delta is for all the buses except the slack bus, for which we already know the angle. We, as we said earlier, since the slack bus can be taken as a reference, so delta 1 is normally taken as 0 degrees, and so we have from delta 2 to delta n the voltage angles, and V2 to Vn the voltage magnitude for all the buses except the slack bus. This can be written as fx is equal to Px Qx in terms of P2, which is a function of x, up to Pn, and Q2, which is a function of x, Q, which is a function of x from Q2 to Qn. So, using these we have made the initial guess for the state vector. Now, compute the bus power mismatches delta y 0. Once we know the value, we have made the guess of V and delta, substituting the value of V and delta into the equation for real power and reactive power, we can find out the mismatch using this relationship P specified minus P calculated. with the value of x known at the initial guess, q specified minus q calculated with x at the specified value. So, using this we can find out this delta p and delta q, which is basically our delta y. So, compute the bus power mismatches delta y. Next step is compute the Jacobian matrix J0, that is with the initial guess state vector x, that is knowing all the voltage magnitude and angles with the guess initial values known, we compute the value for the elements of the Jacobian matrix at the initial operating point. Now, solve for voltage error vector delta x, which is delta delta and delta v for the from the initial guess, that is the error vector based on the initial guess. We can find out using, as we have seen earlier, this relationship. Using this relationship we solve for this. Now, this is already known, but in general the Jacobian matrix will be a sparse matrix, just like the Y bus matrix, which is a sparse matrix, because we know all the buses are not connected to all other buses in a large system. In fact, each bus may be connected to just a few other buses, and therefore the Y bus will contain large number of zeros. Similarly, the Jacobian will also contain large number of zeros. These matrices, as we said earlier, are called sparse matrices, and we take advantage of the sparsity of these matrices in solution to make the solution much more faster. So, with this we have completed the Newton-Raphson load flow. Now, in the next lesson we will talk about another version of load flow, which is very popular, which we call fast decoupled load flow. So, with this we end today's lesson. Thank you very much.